Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
The next speaker is Professor Eva Tardos. Eva Tardos is a Jacob Gold-Schumann Professor of Computer Science at Cornell University. She has won many awards and fellowships, which includes Packard Fellowship, Fulkerson Prize, and ACM prizes as well. Tardos' research interest is algorithms and algorithms game theory, and she's most known for her work on network flow algorithms, approximation algorithms, and quantifying the efficiency of selfish routing. Professor Tardos.
So it's a pleasure to be here and great to talk to all of you. It's great to have an audience this size, all really interested in computing and technology. So let me try to get to it and try to tell you a little bit of the kind of research I do and the kind of questions that I try to address in my work. So I guess I started to think about what's usually termed as game theory, or the effect of selfishness, in the context of the internet. So when you think about the internet, it is a total miracle that it works at all. Like somehow we built a system originally called DARPANET, and was built for a small set of users who all shared project and cooperated. And for some reason, we managed to expand it to most of the whole world using it. Many, many millions of people, many, many millions of corporations and different interests. It's not a network that someone manages. It's a network whose components and parts different people manage, and they try to manage it to make that part, or they experience as good as it can be. They selfishly try to actually take advantage of the internet, and yet it somehow works for all of us. There are other systems like this, and I guess one that I'm going to maybe talk a little bit about is the way advertisements are placed and sold. All of these share the property that selfish users who want to take advantage of a system for their own interest can participate, and in a good case, cooperate to get something good done, and in unlucky cases, actually somehow ruin or destroy a system. So because what I do for my research is algorithms and I guess theory of computing, I like thinking of this as sort of very simple theoretical models. So I want to start with telling you sort of what the issue is in a very simple common example called the tragedy of the commons. So tragedy of commons goes that there's a little patch of green grass, maybe capable of, feeding some number of cows, so that they, stay healthy and have milk and all that. And in this village, you should imagine every farmer owns a cow, and they can all put their cow in this grass. The cow can eat the grass and get milk, and everyone is happy. Except, unfortunately, there are too many farmers. And selfishness claims or says that every farmer thinks that, if I only put my cow in the grass, that's only one extra cow. True, there might not be so much grass, but one extra cow will make a difference. So they all can send their cow to the grass, and at the end, there's so many cows, not the way it looks on a picture, but instead all standing on barely any grass left. And unfortunately, none of the cows can get grass because there isn't any left. And in fact, a patch of grass that was capable of maybe well feeding 100, 200 cows got ruined because there are too many cows standing on the grass. Now, this is an unfortunate byproduct of selfishness that's actually very hard in this particular context to mediate. Like sometimes you put out some fee or count the number of cows, but at the end, the extra person whose cow is not on the grass is very much interested in putting his or her cow also on the grass. There's not much you can do about this. So a more in a theoretical model, you can set up a model, but it's sort of easy to imagine that whatever you're thinking is like the value of feeding a cow is decreases as there are more cows around, so congestion is bad for the cows, and at the end, there's no value left for anyone. So I'm going to start by telling you a sort of positive story that's more internet-related, and then I'm going to use that morale we learned in a different context in sort of selling or bidding for advertisements. So a good example is that I started to work on my research is had to do with traffic routing, and depends whether you want to think of the common Indian experience of overly congested roads, or you want to think of technology and the internet and packet delays. Either way, it's a reasonable mathematical model of what's going on, is that you're sending little thingies, either cars or packets, on some path, and if there are a lot of other thingies around, there are too many cars or too many packets, then there are incredible delays and buildups can happen, and traffic might get really slow. So this is one of those cases where every packet or every car driver would like to go and get his packet or his car to destination as fast as possible, and is not interested in an overall system performance. It's interested in just, me. I want to go home and I want to get there fast, or my packet should get to the destination fast. My browser should download all my packets fast. So first thing I want to tell you that there are dangers here. Let me use the car example because that's a clean and nice example. So imagine there are these highways that you see here, and you should imagine that those big long roads in orange are big wide highways. Even with all the Indian congestion, they just never got congested. Maybe this doesn't happen in India, but some places, occasionally, people build highways that are just too wide and there isn't enough traffic. So maybe they take an hour to travel, but it's independent of congestion for the simplicity of the example. In contrast, those little roads, those are more typical Indian roads. And say, again, for a very simple mathematical model, it takes you 10 minutes to travel there if you're alone, but every car that you share the road with will add an extra minute. Again, it's a little simple. So, 10 cars will take 20 minutes, 20 cars will take 30 minutes. The more congested it gets, the slower you get across. Okay, very simple example. And there is 50 cars. Now, what would happen here, normally you would expect that the 50 cars nicely divide up 25-25 on both directions, generate an unfortunate congestion of 25 cars on each of these roads, and in total takes an hour and 35 minutes to get across. Okay, so what I set up here is a very simple mathematical model of how you model congestion, and that applies both in car traffic and actually has been used in civil engineering since the early 60s as a standard model of traffic engineering, but also applies to some extent or almost identically to packet traffic. Similarly, packet congestion is a function, or delays is, of course, a function of congestion. I'm using a very, very simple function, like a linear function, 10 minutes plus the number of cars, but you can imagine that more complex functions actually pretty well describe what's happening in sending packet across. Here is the unfortunate fact. Maybe some nice person wants to take your network and make it better and puts in this super speed highway in blue. This super speed tunnel takes 0 minutes. It's instantaneous. It's a tunnel under some big hill. You just get across in 0 minutes. And now you should think about what happens to the traffic. And something really unfortunate is happening. Everyone, all 50 of them, will want to use this path. So in particular, let me get back to why they're doing this. The new traffic pattern will double the congestion on every edge, and in fact has increased total delay. Remember, it's 10 minutes plus congestion, so all 50 cars go on that path. That takes 60 minutes to get across this unfortunate blue path, and they have to pass 2 of them, so now that's 60 minutes plus another 60 minutes, that's 2 hours, as opposed to an hour and 50 minutes, hour and 30 minutes we had before. And somehow there's not much, like in the tragedy of the commons with the chaos, there's not much you can do about this. Because every single car traveling this hour and 2 hours they could instead try to go back to the original path. It's not going to help them. So what happened here, which is called the Braess paradox, Braess is a German scientist who realized this paradox, that someone put in an extra road and traffic got worse. Not because anyone being stupid. I guess we're globally stupid as a society. Okay, this Braess paradox has been around for a long time. In fact, has been observed in traffic pattern in different big cities like Los Angeles, for example. It does happen occasionally, and you have to be careful or try to be careful to avoid it. And what I want to think about is, as a computer scientist and actually going away for car traffic and thinking about packet traffic, what are you supposed to do about this? And actually, how bad is this? Is this like a tragedy of the commons where it's completely going to ruin your experience? Or is it instead, you know, it's a little bit worse if you can avoid putting in super speed highways at the wrong place? That would be, of course, cooler, but maybe it's not that bad. So what are you supposed to think about? So what are we learning from this Braess paradox? We certainly learned that there's dangers out there. If you put highways in the wrong place, life can get worse rather than getting better. A very simplistic and maybe traditional algorithmic view would be that we should direct traffic. We should tell traffic which way to go. And in the car context, this just doesn't occur to anyone. I can't monitor there and tell you that if you want to drive to Bangalore, please, you need to go on this road and not this other road. That's just not physically an option. In the history of the internet, it did occur to people to try to apply this message to internet traffic, not very successfully. So the common message is, this is just not viable. This is too giant an optimization problem. And controlling people, whether either cars or packets, to actually do this kind of control is just not the right message. We can't do that. So once we accept it's not an alternative, then it turns out it's really handy that, actually going back to my previous message, is that maybe this paradox is not so bad after all. Life got a little worse, but maybe there's a natural, simple way we can mediate this. And here is, again, a mathematical model with a paper I wrote with Tim Ravgarden by now, actually more than 10 years ago, which says that one way to mediate this is to design a network to carry double the traffic. Now, in car traffic, this is kind of hard. Making your highways twice as big, I understand that's always a big problem in a city, but in the internet, it's ample viable. And in fact, that's the right internet conclusion, and that's how we have been building the internet so successfully. If we put enough pipes down the ground, this selfish business is no big deal. So what this message says, that if we have enough capacity around, enough capacity that with directed traffic, which I promise you we won't actually do, we could even carry twice as much traffic as what we have today, then the fact that mediates the Braess paradox, the fact that people are driving selfishly and possibly ruining things, never going to be that bad. Okay, so this is a very nice case where some engineeringly doable or carryable act of putting down more capacity did help mediate the bad effect of selfishness. Again, it's more viable in internet traffic and much less viable in car traffic. So this message that something simple that one can do is a better remedy than central optimization is much more broad than car traffic or packet traffic. And what I want to do as a more recent piece of thing that I and some other people in the community have been working, research community have been working on, is trying to apply this to the other example on my opening slide is selling advertisement. So as you all know, the internet is free, and there is no such thing as free lunch. So in some way or another, we're all paying for this differently than paying for the internet. And the way we're paying for this is we're watching advertisements. An effective way of selling and displaying advertisement has been a big deal, and that's sort of what pays for a lot of the internet services. There's a lot of advantages to selling or advertising over the internet because you can target your advertisement infinitely better than in a newspaper or a billboard. But this only works if we have good way to actually help people put the advertisement where it's most effective. So let me start with, again, a simple example that maybe many of you have seen around, is the classical, beautiful example of how you traditionally sell something is a single item auction called a Vickery auction, or maybe second price auction. And the way it goes, and in my example, I guess you're auctioning off this apple, and I guess it's a very valuable, expensive apple. People value it at multiple dollars value just for silliness of the example. And these numbers I have on the slide are supposed to be the values people have for this. But unfortunately, of course, you rather get the apple cheaper if possible, so maybe they won't want to tell you the values. And the classical story goes that what you're supposed to do is hand the apple to the person that values it at most, which is, I guess, $7 in my example, but don't make him pay his actual value. Make him pay what's called the second price, the second highest value. That means he's going to extract some bigger utility for this. He valued it at $7, but he only had to pay $5, so gets a value of 2. We handed it to the right guy that wanted the apple the most. And it has these nice properties where the key one that usually gets emphasized, that it's truthful. Now, truthful here means it's in your interest to admit your real value. And you can think about it for a second, and it does sound good. Like, if your value is, well, actually not 7, but 10, and maybe you try to, what's called, shade your value, say a lower value so as to pay less price, it's not helping you. You don't actually have to pay what you named as price. You have to pay the second price. If you shade your value too badly, it might even hurt you. So there's no harm here in admitting your true value. If you're the highest, you're going to get it, and you don't have to pay that. And if you're not the highest, then you don't get it anyhow. So this is usually the sort of classical benchmark or beauty, of auction theory. And there are all kinds of extensions to very complicated setting. I guess this thing called combinatorial auction, when instead of one apple, you want all kinds of fruits. And people have values for packages of fruits. And again, the same system. People are asked to tell their values for different things. And then some central mechanism assigns it to everyone to the package so as to maximize everyone's overall value. And then there is a complicated formula for paying the price. I fleshed this up, but I certainly don't necessarily want you to read this. So this is sort of the classical design of how people think about auctions. And what I'm going to want to convince you in the next couple of slides, that this is a really bad way for the internet. This is not how we ought to sell things in the internet. And before I do that, let me actually open this by, despite this beautiful theory, it's not how things are sold. Not even in the internet, but not even in other things. Like, for example, the certain airports using auctions to sell landing slots to airlines, even they don't use it. So this theory has certain gaps. And I guess I'm basically claiming that while truthfulness sounded good when we did simple item auctions, this more complicated truthful things is actually not what we need. So to start with, having people announce the complicated value system for every subset of fruits of how much dollars they value it, that's very complicated. It's an awful lot of communication. It's a lot of work for these companies to figure out how much they value it actually. Even worse than that, users tend not to know how much they value even a single item. In fact, if I ask you guys how much you value a basket of beautiful figs, some of you might say, yeah, figs would be cool, I'm hungry, I would like to eat some figs. But you can't actually usually put a number on how much you value those figs. So that's a hard exercise to know how much you value something. Leads to mechanisms that are rather complicated, which is the previous slide was trying to indicate to you by just fleshing it up. And actually, maybe worse than this, is this thing really true? Is it really a good idea to admit your value? So remember, I actually went through the mathematics, at least sketching it, convincing you that it's okay. But it's okay only if your sole purpose in life is to eat or not eat that apple. If the only thing you ever do is that apple. If your life is more complex than that, and you're going to do other things, in this example, it's a house. If you're going to do other things than that, that might not be true, might not be a good idea. So for example, before you're buying a house, you might actually, in case you didn't actually win this house, you probably still want a house. So you're not going to bid on another house afterwards. Leaking your value tells, oh, this guy is really rich, we better give him a big price, may or may not be a good idea for you. It's not even good if there's simultaneously multiple auctions going on. There are two houses, you're bidding them on both. Telling your real value can actually be really problematic. So one way I would express this is that this truthfulness, the concept of truthfulness, is only in isolation. When we try to compose it with multiple things we do in our life, it's not working. So truthfulness seems like maybe not the right kind of thing. And again, remember on the internet, these advertisers sell ads, at millions a second, so there are a lot of them and a lot of compositions going on. So what does Econ tell us? If you took a class like what in the US would often be called Econ 101, then they would tell you that there's a clear solution to this. What you're supposed to do is price. Everything has a price, and I just tell the users when they showed up that, hey guys, here are the prices, please tell us what you want to buy. This works very well when you know the prices, and I guess it works beautifully when you know what the prices are, and in fact, there is this beautiful theorem out there that says that if you set the prices right and the market clears. Now, what does it mean the market clears? It means two things. One is that everyone, when it saw the prices, they figured out what they wanted and there wasn't a shortage. Okay, if market didn't clear, if the prices were low, everyone went in the store, they all wanted to, or not in the store, in this case, wanted to buy houses. You all said you wanted that blue house, then the market didn't clear because there was a congestion on the blue house, which wasn't enough. In contrast, market also didn't clear if the prices were too high, because then everyone went to the store and says, no, I don't want anything, this is very expensive. That's also not good. Market clears if everything sold exactly once, which is kind of a magic kind of pricing. I have here a slide to convince you, which is the only maybe more mathematical slide I had, that if you find these prices, then the market clears. That's indeed beautiful. It has the property that the way we allocated the goods optimizes social welfare, optimizes everyone's happiness. So the way the proof goes, suppose you had these market clearing prices, then everyone could get the socially optimal product. They might not. If they don't, they must be getting something that's even better for themselves. You add this up over all the users, and most magically use the fact that the market cleared, so the sum of the prices in this summation nicely cancels, and what you get is the way goods got allocated is at least as good as the optimal, that is, it is actually optimal. So prices are indeed beautiful, and in fact, we use it all the time in our life. If you go in a store, that's what you do. The goods have prices and you buy them. And the stores are in fact living on that this is market clearing. If the store isn't the prices aren't market clearing, either it racks up on the shelf and no one wants it, or there's constantly empty shelf there. But in the internet context, these prices are really hard to find. So I don't know how to find market clearing prices. It's easier to do it on standard products like bread and milk, of which we have a lot of. It's really hard to do it on advertisement. An advertisement isn't actually your eyeball watching this, but it has to do with who you are. Are you someone who buys a lot of stuff on the internet? What time of day it is? Is it the kind of time of day that pizza might be really tempting for you? Is it not that kind of day? Geographic data. Are you a university student near a university, or are you in someplace else? Are you in the US or are you in India? All kinds of things about you. That is, every time they want to sell an advertisement, more precisely, might want to sell your eyeball for watching the advertisement. It's a different selling item, and it's very hard to price all this stuff. And actually, because I'm a theoretician, I felt obliged to put this down here as the last point. Market clearing prices are not guaranteed to exist. When they exist, and when we can find them, they're beautiful, but they tend not to exist. And even when they exist, they're really hard to find. So here is what I'm proposing, and that's actually a much more recent research with a student of mine, is certain natural mechanisms, price-based or bidding-based mechanisms, create approximately market clearing prices. They don't create exactly market clearing prices for two reasons. First of all, because they might not exist. And second of all, because the mechanism is not, we don't know, as bidders or participants in these systems, we don't know enough to create the exact market clearing prices. But they create approximately market clearing prices. And what's going to be nice about this, that when you approximately market clearing, then you're approximately optimal, which is kind of nice given a system and our general sensibility, at least on the internet, and that approximately minimizing time, approximately minimizing cost, with a simple enough mechanism is probably what we want to do anyhow. Okay, so what do I mean by approximately market clearing? As a reminder, the real market clearing, the main important part in the proof was that there are a set of prices and that every participant, if he wants on these prices, can grab his optimal set of items paying this current set of prices, and then the market clears. Instead of this, this requirement, I want to require something that the player can do something, bid something or make a bid or do something that gets his benefit not exactly as high as what I had in the market clearing prices, but approximately that high, and I put in two fudge factors, getting not quite his value and paying a little bit more than the price. You should imagine that lambda is less than 1 and mu is above 1. You pay a little bit above what you should have paid, and you get a value a little bit less than what you could have gotten, but something approximately the same. And the main theorem here, so for example, just to get you an example of what kind of mechanism can have this approximately market clearing property, to very surprisingly an auction system that's maybe not that great already has this clearing property, the single item, the first price auction. So first price is the variant of what I showed you. The second price where you pay your price. What you named is what you price. A lot of things are sold, contracts are usually sold on first price. You bid, and then the best bid you take, and that's the contract. Single price is not truthful, which is why it makes a good example, and I can do it on a single item. So here's a simple example. I tell you you're supposed to bid half your value. Now what does it mean you bid half your value? Well, if you bid half your value, there are two things that can happen. Either you win the item, and because you bid only half your value, the other half is left for yourself. You shaded your bid properly, it was first price. Admitting your real value would have been dumb of you. Or you don't, in which case the price was high enough, and either way, my funny inequality is true. So either you win, in which case your utility got pretty high, or you didn't win, but then the price that someone else paid must have been high enough. So this is a simple example of something that approximately have this market clearing property. So our theorem with my student is that if something has this approximately market clearing property, then it's also approximately optimal. I didn't write the proof down here, but it's virtually identical to market clearing proof. The only thing I'm losing is because I have these fudge factors, the result will have the fudge factors. That is not exactly optimal like it was for market clearing, it's approximately optimal. But what's nice about this, that unlike the market clearing, which had to be only true if you actually found those market clearing prices, this actually is very flexible. It's not only true if you found an equilibrium, which unfortunately might be equally problematic to find, but instead it's true if people learn or non-reach an equilibrium in a natural kind of repeated play. So that's maybe the last thing I want to tell you a little bit about is, so what do I mean by it's true even without reaching an equilibrium? So here is how bidding really works. There are these companies who want to sell things, and they start learning. You're a little company, a little mom and pop store. You decide to start advertising. On day one, you're rather clueless. You put in some bids, you see what happens. You get some sort of outcome. You run the auction, you get the outcome. Day 2, again, something happens. You run the auction, day 3, day 4, and so on. The idea is that in the beginning, you were clueless. You didn't know what's going on. And in all honesty, there are many beginnings. Because even very experienced companies like Microsoft, something sometimes changes. The world changes. Some interesting thing happens. And somehow everything behaves differently, and you have to adjust. But whatever you're adjusting to, hopefully after a while, you have a good idea, and you start being better. Now, what do I mean by being better? What I mean by being better is I want you to have the following very simple property, which I think most people are good enough, and certainly algorithms are good enough to reach this. To watch if there was a strategy with hindsight that would have been really good all the time, and do it. You don't have to be super good. You can change your bid, you can change your behavior, but if there is a wise strategy with hindsight, then please watch and be at least as good as that strategy would have been. In fact, you can be a lot better than this. It could be the case that bidding only in the mornings is much wiser than bidding all the time. In the afternoon, skip that. This is a product that people only buy in the morning. That might be even better, but at least please be as smart. If there is a single strategy that would have worked beautifully, do it. In fact, in the context of the first price, I even can tell you what the strategy is. You can do whatever you want. Shade you with more than half the value or less than half the value. But I give you a strategy that is half your value. If that strategy is better than what you're doing, you were pretty non-smart in your bidding. I told you what to do. You don't have to do it. But if my advice is a lot better than your behavior, you're not very smart. Okay, so this is the standard I want. I want it, in many cases I can do what we're doing here in first price auction. I can name the strategy. You don't have to do it. I just give you advice. And I'm assuming in my theorems or my analysis that your behavior was at least as good as my advice. That is, there's a low law of t, that's an error factor there. Your behavior wasn't much worse than my advice. Again, you're not obliged to follow my advice, but you have this advice in front of you on a computer screen, and if your outcome is a lot worse than the advice, sooner or later wake up to this and follow the advice instead. And if we do that, we get the same quality loss as mu over lambda. So again, it applies to learning outcomes. And what's nice about this, and I won't go into the details, this actually has the beautiful benefit that, unlike truthfulness, this composes. If you participate in one kind of auction in one hand, and buying a house in one hand, and going shopping for your fruit on the other hand, and they both have this property, then the composite will preserve this property. So this has the nice property, which is something we all want, is that any of the economic activity we all do in our life, whether it's selling advertisements or driving to work, we never do any of those in isolation. We all do this as part of our bigger life. And what's nice about this notion of approximately market clearing mechanisms, that they do compose. That is, they have this nice they preserve this property when you're participating in multiple auctions. There are a bunch of this kind of mechanisms around, and I guess I gave you the example of first price auction, which was a simple example to use. I should admit, first price auction is actually better than this half-half that I used is a silly simple numbers to use. You can do better if you're a little careful. The generalized auction that internet advertisement usually sold on also has this property. All kinds of public good auction, bandwidth allocation. Maybe an interesting example I want to spend a second on that also has this property is what's usually called all-pay auction. So all-pay auction, all-pay auction, as the name says, everyone pays, and the guy who pays the most wins the award. It's a very painful kind of auction. The common example of all-pay auction is crowdsourcing contest. Okay, when you're crowdsourcing, like, you're doing a competition for who's going to design the logo for this university. I don't know if the university would like, or the hotel would like a crowdsourcing for the logo. What usually they do is they announce a contest to have a logo contest for the hotel, and the guys whose logo they adopt is going to get some big award, and everyone else gets nothing. Now, no one paid anything, but you paid with your sweat. All the participants who submit logos spend effort and energy, which is sort of money, in participating in a contest. That's a typical kind of all-pay auction. There's one winner who won the prize, and the rest of them win nothing and effort and put energy. So all-pay auction also has this property of approximately market clearing. And remember, there were two parameters which I put on this slide. So in conclusion, what I try to convince you of is that life around us is full with places when we all, or the humankind, participates in a shared activity, from actual markets, from the internet, from traffic routing. And in many, many of these cases, the shared activity, we all participate in order to extract some good for ourselves. So here I'm thinking of examples only where your goal is to make life good for you. I'm not trying to, in any of my examples, I wasn't trying to hurt the other participants. I'm just trying to help myself. But even this can lead to what's called the tragedy of the commons. That is, it's possible, and in fact not uncommon if you're not careful, that it leads to a design setup where everyone a little bit optimizing for themselves really hurts the common good, and you end up with a ruined society, whether it's a park that's not usable because everyone left one piece of dirt in there and it's now a mess, or the grass that's not usable because there were too many cats on it. But what I mostly did with my technical part of the talk is try to tell you that in many setups, with low care and careful design and thinking about the principle, we can design things so that the effect of selfish use get mitigated with the right kind of design. So I did this in the context of the internet by having enough cable, and in context of selling things or markets with this approximately market clearing style mechanisms that have the property that the right thing will happen without exerting so much control. We don't collect all the values. We don't have a central entity dividing out the goods. It's all a natural bidding, and you get everyone bids on different items. A distributed kind of property. It's easy to manage, and nonetheless, the outcome is reasonably good. In most of these cases, in both cases that I showed you, reasonably good here meant you lost a factor. I mean, a factor of 2 in both of my examples. You're only half as efficient, and you had to have twice as much cable. But in many contexts, especially when time is what we're talking about in context of internet and technology, a factor of 2 loss is well paid for by the efficiency of a simple to manage system. Yeah, there's no central control, and it's simple to manage. And I'm going to stop here, and thank you very much.